Hello everybody, my name is Mathilde Lemang. I'm a device integration lead in QphoX, and today I will present the quantum modem, or the gateway to scalable quantum computing. How do you... Yes. So as you might know, so a big challenge for classical computing is polarization, because it's really important matter, and it's even more important for quantum computing, since it's more difficult to do, and it's more difficult to build and to control. And for single system quantum computers, one of the main challenges is that the processor size is limited by heat load and spatial constraints. So for the spatial constraints is that you need to access the qubit with coaxial cables, and the heat load comes from these coaxial cables, but also it comes from amplifiers. And for multi-core quantum computers, one of the main challenges is that currently there is no way to interconnect quantum computers beyond the cryostat at a large scale. So everybody wants to make smaller, high-fidelity quantum processors, but they all need to be connected into a large parallel quantum processing unit. And this is where we are at QphoX with our quantum modem. So here you can see that there is a quantum processor in a cryostat fridge. And you need to bring the information from the cryostat to room temperature, and you can use for that the quantum modem and optical fibers. Here on the side, you have like two quantum processors connected to each other, but you can extend to several quantum processors. And with the quantum modem, you can link all the machines, whatever the technology or the manufacturer. To go closer on the quantum modem, so we are doing the world's first commercial transducer for low loss and high fidelity transmission of quantum states. And our devices have really nice properties since they are fully integrated. They have a large bandwidth, large repetition rate, high efficiency, ultra low noise, and minimal heat dissipation. And the quantum transducer is based on the coupling of the microwave and optical phonon through a mechanical intermediary resonator. So you have electromechanical interface, which is a piezoelectric, and optomechanical interface, which is a nanobeam of silicon patterned with holes. Here you have a microwave resonator. The microwave resonator is a wire patterned with a ladder, and it's tunable. So you can adapt the frequency of the microwave resonator to the frequency of the mechanics. And the microwave resonator is also an impedance match to a 50 ohm transmission line. So it makes the quantum modem also modular. Then you have the piezoelectric. Here, it's a small block that is blinking. And the piezoelectric has a really strong piezoelectric coupling. So the piezoelectric generates mechanical vibrations that leak into the nanobeam. The nanobeam here is designed to hold a mechanical breathing mode at its center. And then you can send an optical photon in the waveguide. Since it's because of the proximity effect between the waveguide and the nanobeam, you can have evanescent coupling, and then the photon can swap in the nanobeam. Here you have the phonon state, which is coherently converted in a photon state, and the photon can swap back in the waveguide and go out in an optical fiber. So this is the concept of the quantum modem, and I will show you our results. So our first paper came in Nature Nanotechnology, and here you have an image of the transducer and an image of the microwave resonator with the transducer. So first of all, what you need to do is determine the properties of the transducer. So you measure the mechanical resonance frequency, you measure the optical resonance frequency, and you measure the mechanical resonance frequency, and this you do it at millikelvin temperatures. Then you continue the measurement, and you can check what is the interaction between the microwaves and the mechanics. And you get this anti-crossing, And this anti-crossing suggests that you have high interaction between the microwave and the mechanics. And also, it suggests that you have high efficiency. So then you do up conversion. So you convert your signal from microwave to optics. You do down conversion. You convert your signal from optics to microwave. And thanks to up conversion and down conversion, you can calculate the efficiency. For our first paper, here you can remember that the figures of merit are that we have high efficiency, almost 1% at 1 microwatts power. We have low added noise of 6 photons, a high repetition rate, 100 kilohertz, a large bandwidth, 15 megahertz, and our devices are scalable because here the footprint is 0.15 square millimeter. Then remember earlier I was telling you that you need to access with microwaves inside the cryostat. So here you can do optical control. Well, you have a laser that is modulated, or different lasers that are modulated with microwave control signal. And you can combine all these microwave control, all this laser with into an optical fiber. And you can combine several microwave signals with different frequencies. Then you bring this optical fiber in the cryostat, and in the cryostat, you extract all of them. You can do optoelectric, you can do transduction and convert the signal in microwave control signals thanks to optoelectric transducer. Conversely, you can do optical readout, where you have microwave readout signal. You convert them thanks to electro-optic transducer, and you put them in an optical fiber. You take the signal out of the fridge with an optical fiber, and you extract all this signal to do optical readout. What you need to remember here is that the transducers are compatible with multiplexing technology and standard telecommunication technology. And then, if we continue with optical readout, we published recently a new paper on the archive where we do optical readout of a superconducting qubit from Rigetti. So here you have the setup with a microwave source, qubit with a readout resonator, or transducer, and microwave and optical readout setup. So here you can send a signal that will take the state of the qubit, and you can do classical microwave readout, and you get a fidelity of 0.73. And if you do the same, but this time with optical readout, so same process but with optical readout, now you get the information about the state of the qubit, and you have transduction, so the signal goes through the microwave resonator, the nanobeam, and then you can read it with optical readout. And this time you get a fidelity of 0.63. So here, what you need to remember for this second paper is that we managed to get high efficiency of 3% with 1 microwatt average power. The qubit properties were preserved, and we had a fidelity of 0.63, which is a first step towards a high fidelity optical readout. And now I would like to thank all of you for listening to my talk, and I would like to thank all my team. You can see that we are a really diverse team. If you're interested to join us, we are hiring, and I would like to thank all the investors, people who are funding us, and our collaborators.